Okay, folks, so we just recently tried to get into a formal understanding of a thermodynamic analysis called the change in enthalpy, which is a quantitative amount of heat that goes in or out of a system, whether through chemical change means or physical change means. It really fundamentally doesn't matter. It's just basically joules of energy in or joules of energy out. So the second of our thermodynamic analytical takes that we're getting into this week is the idea of entropy. And this is a word that has come to take on so many meanings in the last 150 years. This word applies not just to chemistry and physics. It's used a lot in information systems and business, and then metaphorically in poetry even. But we're going to stick with sort of the original rigorous physical and chemical understanding of the term. But believe me, you will encounter this term in many other contexts. It's sort of intuitive but mysterious at the same time. And so, of course, it fascinates people both on a scientific level and on a sci-fi level. So entropy is basically a way of representing a couple of our laws of thermodynamics, the second and third ones in particular. So what it's saying is entropy is doing is it's helping us understand quantitatively the spontaneous flow of energy from high concentration to low. Is that energy will always move from a hot reservoir to a cold reservoir, hot region to cold spontaneously, never in the reverse, never without the addition of outside energy from the system, or in an artificial sense. And there's also this understanding that is implied in the second law of thermodynamics is that when this flow spontaneously happens, energy is lost to the system and distributed out into the universe. So on a universal scale, energy is always becoming more distributed out, more spread out, more microstates, more possibilities of where that energy goes from that concentrated system out into the universe, whether that energy was the heat from the cup of coffee or from the chemical reaction or what have you. So in a quantitative sense, we can always kind of get this foundation for analyzing, what do we mean, how do we count this entropy? The third law of thermodynamics gives us this starter value, this starting, start from zero thing, and that is absolute zero Kelvin, which is this point where there's basically no pressure or temperature in the system, and basically the system is something that is this idealized crystalline solid. It's just so stable and perfectly packed and ordered. This is probably somewhat more idealized than literal, but let's say that it is true. So in other words, that system only has one possible microstate. It's not moving, there's no real kinetic energy reshaping it or moving it around or making it flow. It's like the idealized block of ice or whatever. So if we start from zero, absolute zero, we can, as a reference point, we can thermodynamically analyze how much energy is being distributed as we warm something up, or as that energy leaves it, so to speak, and it cools down. So we have this very famous equation that was put together by an Austrian scientist in the 19th century named Boltzmann, and that says that the entropy of a system is a constant. We call this Boltzmann's constant, 1.38 times 10 to the negative 23rd joules per Kelvin, times the logarithm of the number of microstates of the matter in the system. So a microstate is kind of like, if you had this snapshot of how all the matter was, in terms of arrangement, that's one microstate. And then if any of those molecules have moved in any way, well, that's another microstate. And of course, so we're talking billions of them. So if we have this idealized at absolute zero crystalline solid, well, that's one microstate. The natural log of 1 is 0. So in other words, we would have entropy of 0 would be at this idealized state. Anything warmer than that, we're going to be quickly multiplying entropy. So one cute little thing I thought I'd kind of point out, they never told us this in high school, is when we get into that gas laws next week, we are going to be using the ideal gas constant to analyze the pressure and the volume and the energy and the amount of molecules of a gas. And then if we take Avogadro's number, 6.02 times 10 to the 23rd power, and we multiply it times Boltzmann's, we get the ideal gas constant, 8.31, which we'll be using constantly for the rest of the semester. So that's a little bit of sidebar, but I just did want to at least mention that, how those two numbers gel. So let's go ahead and now move on to what do we mean in practical sense, like in a chemical reaction or a physical change, a change in entropy. We'll go ahead and look at it on a micro scale of one molecule or one chemical equation. And so they'll start becoming a little bit clearer to us before we move on to the macro scale, where we actually start running some calculations.